This video is all about exploring the solar system. Yes, and in this video we're going to look at lots and lots of topics. It may be too small for you to see because there's an awful lot going on here. Basically, we're going to start by talking about things like planets, things like comets, things like dwarf planets, asteroids, all that sort of thing. Then we're going to talk a little bit about how you make observations with telescopes, and then it finishes with some stuff about landing on the moon. So there's a huge range of different areas where this video is going to take us. And because it's such a long topic, I'm hoping it's not going to be too long a video, but I suspect it's going to be. But that means I'm going to have to go fast. So let's start with that first point about knowing the names and relative locations of these bodies in our solar system. In fact, you don't need to know them, you just need to be able to use knowledge of them. So what we've got here is some dwarf planets series, my personal favourite of the dwarf planets, although obviously Pluto is a popular one. And then this is a little graphic showing what those dwarf planets look like in terms of sizes. And some of them, like Halme here, is a very interesting shaped one with a ring. This is pronounced Maki, not make. So there are some dwarf planets. So you could be given data about these and then have to use them. So it's a good idea to have some idea of where these dwarf planets are. With the exception of Ceres, the rest of them, they're all Kuiper Belt objects. Ceres is in the asteroid belt. So I've got some more pictures here because pictures are great. Here's Ceres and a bunch of other things found in the asteroid belt. You can see there's a large asteroid there, Vesta. That's the largest asteroid, just about the largest asteroid. Ceres was a planet when it was first discovered. It was called a planet. Then it got demoted to asteroid, which makes me chuckle a little bit that people were so upset with Pluto being demoted from planet to dwarf planet. And yet Ceres was demoted from planet to asteroid. That's a far bigger fall from fame. Here we've got some other beautiful pictures of comets. In this case here, this is Hale-Bopp, my favourite comet, because I remember seeing it so clearly in the sky. Okay, so what could that data look like? Well, it could look a bit like this. So here you've got the planets, so Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Below that, we've got the dwarf planets, and below that, we've got the asteroids. And there are far more dwarf planets and asteroids that I could have included. I'm just trying to give you a feel for what those data might look like if they're presented to you. So here we've presented what's called the semi-major axis. The semi-major axis of an ellipse is sort of like a radius, but it's the longest radius. A radius, the word radius, only applies to circles, and a circle is a type of ellipse. So the semi-major axis is from the centre of an ellipse to the point on the ellipse that is furthest from the centre. Sort of a maximum radius, but that's bad language because it's not actually a radius. So you can see for the Earth, that's 1.00, and the Earth's orbit is almost circular. And you can see these. Essentially, it's how far away from the sun these planets are. That's what that is. It's in astronomical units, which is why the Earth is being given 1.00. It is one astronomical unit from the sun by definition. We've also got here some comets on this table. You can see here the data is slightly different. We are given a semi-major axis. We are also told the eccentricity. Now, the eccentricity tells you how squashed the ellipse is. An eccentricity of 1 is a circle. So anything less than 1 is a squashed ellipse. You can actually get eccentricities greater than 1, but then they're no longer ellipses. They're other conic sections, and we don't really need to go into that in this video. So you can see here this comet third down on the list, C/1999S3. It's almost a circular orbit. You can also see from the semi-major axis that it is only just under 19 astronomical units away from the Sun. We're also given here the period. That's how long it takes to go around the Sun, and this is given in years. And the next perihelion. This is when it is as close as it can get to the Sun. This is the next time when that comet will be as close to the Sun as possible. So that's what the data may look like in the table. Let's have a look at some of these dwarf planets then. Ceres, you can see that's not too far away from the Sun compared to all of the others. Well, that's because the others are trans-Neptunian objects. They're in the Kuiper Belt, whereas Ceres is found in the asteroid belt. And I mentioned that before. You'll also notice Sedna is quite a long way out, over 500 astronomical units. That's further than Pluto. It's a very long way out indeed as a dwarf planet. You might even say that's not actually a Kuiper Belt object. That might even be an Oort Cloud object. I'll have to check the list a bit later. And we've got our asteroids here. So that's what the data may look like. So using names and relative locations, well, the names are just on the table, and you should recognize the planets. You should sort of have a recognition of dwarf planets, maybe the big ones like Ceres, Pluto, Eris. You've also got my favorite one to pronounce, Maki. And then things like Vesta as the asteroids. That's the biggest asteroid. Okay, so let's dig into comets a little bit and have a look what comets are all about. Comets have different parts to their structure. They look a little bit like a falling star, but actually they're a little bit more exciting than that. So with a comet, you can see a tail when it is close enough to the Sun. You can't always see a tail when it's not close enough to the Sun. But in fact, there are two tails that you could see. There's this tail here, which is labelled gas tail, and this tail here, which is labelled dust tail. If the Sun is over here emitting light, which is going in this direction, the gas tail doesn't change direction very much. It sort of points in exactly the opposite direction from the Sun. The dust tail, however, that flows backwards a bit because as dust is leaving the comet, it's moving slower than the gas is leaving. So as the comet moves around, it sweeps this tail behind it slightly. So the dust tail will always go slightly behind the direction that the comet is moving. It also says dust trail here, but we don't really need to worry about what that is. We can work that out from the diagram, but that's not a part of the comet that we're interested in. So here's a schematic, a diagram breaking down those different parts of the comets, and you can see you've got D here, the dust tail, which sweeps backwards because the comet is moving in this direction here. We've also got this light blue section here. That's the the gas tail. Here it's labelled gas or ion tail. It could be called either thing. I actually learnt it as ion tail. So the ion tail coming directly away from the Sun. G points to the Sun. The Sun is over here in the direction where G is. But if we look into the comet itself, we've got the very middle part here, which we refer to as the nucleus, in the same way as we refer to the middle part of a biological cell as a nucleus, or refer to the middle part of an atom as a nucleus. The middle part of the comet is the nucleus. Around that, you've got this coma. This coma is a region of material that's just away from the middle of the comet. That's all it is. Even further than that, you'll have other parts to the comet. I don't know if they're labelled here. No, you've got sort of layers of atmosphere of the comet as you move a bit further away. But the bit of the atmosphere of the comet you need to know about is called the coma. Okay, if you look on this diagram here, you can see there's a part labelled E, which is the hydrogen envelope. You don't really have to worry too much about that, but it's part of those sort of layers of material around the outside of the comet. So there are, broadly speaking, two types of comets. The short period comets and long period comets. The short period comets tend to be found in the Kuiper Belt. That is found around about where Neptune is and a little bit further out from Neptune. Beyond the solar system, well beyond the reaches of Pluto, you'll find the Oort Cloud. We'll talk about that in a moment. So the short period comets, it's called a short period But remember that most of these are coming from the Kuiper Belt, around about where Neptune is. So the period actually works out to be hundreds of years for these comets. You can see on the left here a diagram showing the eccentricity of one of these Kuiper Belt objects, one of these trans-Neptunian objects. And here we've got our map of the solar system. If we look in the middle, we've got the Sun. You can work out what J and S, Jupiter, Saturn, U and N, Uranus and Neptune are. And then around that, we've got a bunch of dots. These are different trans-Neptunian objects. Trans-Neptunian means that they exist beyond the orbit of Neptune. And these are parts of the Kuiper Belt. This is what the Kuiper Belt is. The long period comets, they originate from much further out, the Oort Cloud. So if we've got our map, let's try and show you what the map looks like. It looks a bit like a space station from some sort of Star Trek film. It's not. Right in the middle here is the solar system that we think of. And around the outside, we have a huge bubble of material. So before I said Sedna, maybe that's in the Oort Cloud. No, I was wrong. It's not in the Oort Cloud. It's nowhere near it. So if we work our way around, here's the middle part of our solar system. You know, you've got Earth in there. You've got Jupiter there. And between Mars and Jupiter, you've got the asteroid belt. And okay, let's move out from there. So if that's this little bit in the middle, that red ring as the orbit of Jupiter, is that red ring there, then we've got Saturn, Uranus and Neptune. We've also got Pluto's orbit here, although it's not showing all the interesting things about its orbit. We can actually go further out from this as well. So this is where Sedna is, but the orbit of Sedna goes much further out. The semi-major axis, remember, was more than 500 astronomical units. So that's still not in the Oort Cloud, because that circle, that ellipse, should I say, the orbit of Sedna, here it is, and the Oort Cloud starts, the inner part of the Oort Cloud, around here. That's the nearest part. The Oort Cloud itself has got sort of two parts to it. So you've got this part that comes out like this, named Hills Cloud. Looks a bit like a big flat donut. And then beyond that, you've got this, the outer spherical part of the Oort Cloud. And if you look at some of these distances, the Kuiper Belt's all the way here. There's the Sun, there's the Kuiper Belt right in there. Sedna's are all the way in there. And then we've got these other objects that we have seen around here. Now, it should be animated. Yes, it is. As it slowly scrolls across, you can see that there are comets that we believe originated from various places. There's also labelled here closest approach of various stars. And it's quite surprising to see just how close some of these stars got to the outer parts of the Oort Cloud. Perhaps it shouldn't be. These stars, if they get close to the Oort Cloud, they're going to give a little gravitational tug on the material in the Oort Cloud, which is going to cause the orbit of that material to change. And some of that material, the material is comets, it's what it is, rocks and other volatiles up there very far away from the Earth, very far away from the Sun. But when you give it a bit of a perturbance, you knock it gravitationally by having a star go past, it can jostle some of this around, knock it around, it'll fall towards the Sun. And that's where you get these long period comets from. Don't know if you saw then scrolling across the screen all the way down there somewhere, but there was there was the nearest star to us, Proxima Centauri, was shown on that as well. So it's extending all the way out here is the Oort Cloud. It's a huge region, given that all the interesting bits of our solar system are sort of, buried in the beginning there, around there. Okay, so let's move on to the next part of our solar system then. And actually, it's not quite the next part. It sort of fits in between the Kuiper Belt and the Oort Cloud. And that's the edge of the heliosphere. The heliosphere is the entire region where the sun's influence, the radiation influence from the sun can be felt. And beyond that is outside the heliosphere. And this is lovely little sort of demonstration I think everyone has seen at some point. If you pour water into a sink, you get a region where the water pours away okay when it hits the sink. And then it causes a turbulence, a sort of a region of chaos around the outside. Well, what's happening there is the water's trying to pour down one way, but we're pushing the water the other way from this stream of water coming down the middle. So where the inward motion of that water collides with the outward motion of the water, you get this chaos around here. A sort of a termination shock. That's what it's labelled as here on this diagram. And that's what we get with solar radiation. Radiation from the sun leaves the sun, it's got no problem, but gravity is pulling it back. And at some point, the radiation is going to start trying to fall back at the same time as the radiation is leaving out, and you get this chaos around here. We have actually had two, or maybe one actually, Voyager 1, a probe, pass through that termination shock region and send back measurements from it. So that's how we know it's there, where we predicted it would be. And so here we've got our different planets, Mercury, Venus, Earth, Mars. I don't know what scale this is, but this is definitely not a linear scale. Let's have a look. Yeah, it looks logarithmic to me, a logarithmic scale. So 1 astronomical unit, 10, 100,000, 10,000, 100,000. It's a logarithmic scale. So please don't look at this and think, oh, the Oort Cloud's only there. We're more than halfway to the Oort Cloud. No, we are not. Nowhere near the Oort Cloud. Voyager 1 is not going to reach the Oort Cloud in our lifetimes, or our children's, or our children's children's, or our children's children's, and so on. It's going to be thousands of years. Alpha Centauri sits there, and so on. So that's the sort of the structure of our solar system and the influence of our sun. You've got the Kuiper Belt near the middle, relatively near the middle, so 30 to 50 astronomical units out, just a bit beyond the orbit of Neptune. What does it consist of? Well, rocks and volatiles. Volatiles, remember, is things like ice, but it's not just water ice. It could be ammonia ice or anything else. So you've got your asteroid belt, which is mostly rocks with very little in terms of volatiles. The Kuiper Belt has more of those volatiles in it. So you get some comets there, mostly comets. It's got centaurs, which are kind of like comets, but kind of like asteroids. And there are some dwarf planets in there as well. We carry on out from the Kuiper Belt. We reach the edge of the heliosphere, around about 80 to 100 astronomical units, a bit further out. And beyond that, we're going to say that we're now in the space between stars. We're out of the immediate influence of the sun's radiation. We've sort of broken through that region where the radiation falls back at the same rate that it's being spat out by the sun. That's not a technical term. Emitted, let's say. So you go past that termination shock region, and then we reach the Oort Cloud. And the Oort Cloud is much further out in the space between stars. We believe other stars have these clouds as well. Very sparse, lots of material out there, but it's such a large space that it's quite sparse. Comets, might be some asteroids, maybe 2% asteroids out there, but look at the scale of this thing, up to 200,000 astronomical units. It is enormous. Okay, so the thing about the heliosphere is that it's not spherical. It's not perfectly spherical at all. As the Earth moves round the galaxy, it leaves a tail behind it. So the heliosphere actually has more of a teardrop shape, or an egg shape to it. So it's about 80 to 100 astronomical units in the direction that the sun's moving through the interstellar space, so moving around the center of the galaxy. But behind the sun, it goes much, much further than that. I'm not sure if I've got a diagram to show that. No, I don't. Okay, let's have a look at some planets. That's Mercury. It's hot, but it's a dead rock. It's not that hot on the dark side of Mercury. That's Venus. That's Earth. There's the moon on the right. Earth's the one on the left. That's Mars with its two moons, Phobos and Deimos. I think it's Phobos on the left and Deimos on the right. There's Jupiter. We've got a bunch of moons there as well. We'll talk more about these later. The key thing with these is you have to be able to recognize the planet just from the picture and know roughly where it is. So we all know that Mercury is the closest to the sun, no problem. And then Venus, interesting things about Venus, like the high temperature on the surface, The high pressure, the tremendously corrosive atmosphere, only a little bit smaller in terms of volume than the Earth. There's the Earth and the Moon. We've already talked extensively about the relationship between the Earth and the Moon in previous videos. Phobos and Deimos, we think that they are captured asteroids. The Moon captured them from the asteroid belt because they are just small, irregular shaped rocks. Very, very small. This is not to scale, this picture at all. This one, I don't know, but don't think it's to scale. It's close. Maybe not. This one's not to scale at all. So Jupiter's moons, the Jovian moons, there are lots of them. But here are the four most notable ones that you do need to know. Here you've got Io. Looks a bit like some sort of gobstopper sweet. You've got Europa here. We're all very excited about Europa. Water underneath the surface of Europa. Maybe there's life there, maybe there's not. Ganymede over here, made famous by that song that Lister keeps singing in season 1 of Red Dwarf. And here we've got Callisto on the right. And these are the 4 moons that Galileo saw through his telescope. Saturn has got loads of moons as well, dozens of moons as well. Everyone would recognize Saturn. Uranus and Neptune we know far less about. We're sending probes there to find out more. But at the moment, we don't actually know that much about these worlds. We know what the composition is of the surface, sort of. But there's a lot we don't know. These are 2 almost the same size. So this is the list of the planets where the sizes are to scale. So you can see the sun here, the curvature of the sun, that's enormous compared to these planets. You see Uranus and Neptune are almost the same size. Saturn's not that much smaller than Jupiter, but the rings make it look a bit bigger. Then you've got Venus and Earth almost the same size. In terms of the distance between them, this is what it looks like. So you've got Mercury, Venus, Earth, and Mars all the way over here, where the sun would be at 0. These are in astronomical units. Then Jupiter, Saturn, Uranus, Neptune. They get further and further apart the further out we go. So I couldn't easily do the same size and the same distance all to the same scale. I just couldn't do it because the sizes would be too small. Here are the planets. This is some data. So you might have to read data about planets. Everything on here is stuff that you should either know or be able to pull off a table. So relative size, you don't need to memorize these. Relative diameter, you don't need to memorize these, but have an idea of these. Because size was a bit vague, I've given here the relative volume and the relative diameter of these planets. I thought that was a useful way of looking at it. Relative mass, and then you've got temperatures. Where there's blanks, it's because we don't have information about it. You can see what I said about Uranus and Neptune. We're missing information. Where it says the moon for Earth, there's always going to be someone that says, oh, there's more than just one natural satellite of the Earth. Yes, fine. But we're just going to look at the moon. We're not going to care about teeny tiny rocks that happen to be in orbit as well. Ring-wise, there's some reports that Earth has a very faint ring system. I mean, the rings are going to be absolutely tiny because I can't see them. So we don't really need to think about that. It's only the rings that we can see that we really need to care about. Again, Jupiter, there's reports that's got a very faint ring system, but it's barely visible. When we think about rings, we think about Saturn. Maybe Uranus, but definitely Saturn. Neptune's ring system looks very young. We don't know how long it's going to be there for. It looks unstable. Perhaps a captured asteroid that got smashed up as it got captured or something like that. We're not sure. The atmospheric compositions, you'll notice some of these don't add up properly. That's because of rounding, where I've rounded some numbers. Look at this one. So 80% hydrogen, 19% helium, 2% methane. That adds up to be 101%. Yeah, that's just because of where the rounding was on numbers. So these are approximate numbers. Don't worry too much about that. And you'll notice I don't have the atmospheric pressure at the surface for Neptune. It's a minefield. You can look up data, for the atmospheric composition at different depths. You can look up data for the pressure at different depths, or the composition at different pressures, or the temperature at different pressures, or the temperature at different depths, and so on for these planets. But trying to put it all together is a bit of a nightmare. So this is the data that I'm giving you here. And it's not something, that you can memorize. You just need to get used to pulling data out of tables. So let's talk about the astronomical unit for a moment. Mentioned it before, mean distance between the Sun and the Earth. That's not quite right. It's the semi-major axis of the orbit of the Earth. It's 1 astronomical unit, but there we go, I think. Please correct me in the comments if I'm wrong. So this is to 2 significant figures, how far 1 astronomical unit is. And let's do a conversion. Let's imagine we want to know the distance between Saturn and the Sun, but we want that distance in kilometers. We know that it's 9.58 astronomical units because, go back a slide, we pulled that off this slide here. Where is it? I haven't got it on here. Maybe it's one of these earlier slides here. Where is it? All the way back. There we are, somewhere back here. 9.58. There we go. Let's go all the way forward again. Right, so we know that it's 9.58 astronomical units. We want the answer in kilometers. So do we times or do we divide by this number? Now, for GCSE students, this can actually be quite a complicated thing to think about. So this is what I recommend you do. You always present unit conversions like this. We know 1.5 times 10 to the 8 kilometers is 1 astronomical unit. That means the thing on the top of this fraction means the same thing as the thing on the bottom of this fraction. When you divide something by itself, it equals 1. So by timesing by 1, we have not changed the distance. The distance, 9.58 astronomical units, multiplied by 1 is still the same distance. But by writing the number 1 as a fraction like this, I can see I want astronomical units on the denominator of my fraction so that I can cancel it and be left with kilometers on the numerator. So that's how I know that I multiply it. Whereas if I was given the distance to the outer edge of the Kuiper Belt, 750 million kilometers, and I wanted that in astronomical units, well, in that case, I'd multiply it by the number 1. I'm not changing this distance. Remember that 1 astronomical unit is 1.5 times 10 to the 8 kilometers. But I've written that fraction so that the kilometers is on the denominator, so I can cancel the kilometers and be left with astronomical units as the numerator. Bit tricky. You might want to play that bit again if you're not sure about unit conversions. So the next bit is about meteoroids and meteorites. So remember from a previous video, meteoroids are just very small lumps of rock in space. So what are they? Where do they come from? Usually, we think they come from asteroids colliding and breaking bits off. And that's where the meteoroids come from. So they tend to be crumbly, they tend to be rocky, or they tend to be metallic. It says here silicates, some iron, some nickel. There's some talk about mining these things, so maybe mining asteroids rather than meteoroids. They're not really stable enough for that. So a meteorite, remember, is what we find on the ground after you've seen a meteor. A meteor is what we call the little lump of rock that falls through space, falls through the air from space, I should say. And then what we find left over on the ground is a meteorite, the part that's left behind. What we can do, which is very clever, is look at the composition of the meteorite and try to work out where it came from. Now, I'm not just talking about chemical composition here. I'm talking about the abundance of certain isotopes. Because different planets have different ratios of certain isotopes. Isotopes, remember, different isotopes of the same element have atoms, or should I say the atoms of different isotopes of the same element have the same number of protons in each nucleus, but different numbers of neutrons in each nucleus. So take uranium, for example, about 0.7% of the naturally occurring uranium on Earth is uranium-235. That's uranium, but 235 nucleons, that's neutrons plus protons, found in the nucleus. The rest of the uranium on Earth, the vast majority, is uranium-238, a different isotope. They're both isotopes. Everything's an isotope. So that ratio, if we found a rock falling to Earth with that ratio, we might think it actually originated from the Earth. I'm not sure how that's the case. Or from something that formed around the same time as the Earth. So we can look at the structure and the composition of meteorites to work out where they came from and what that tells us about where they came from. One interesting feature on some asteroids is this Widmanstaten pattern. I believe I'm pronouncing that correctly. The Widmanstaten pattern looks a little bit like this crisscross of these straight lines. They're crystals of nickel and iron that have grown very slowly over time. When I say slowly, we're talking over the course of millions of years. So these Widmanstaten patterns, very sorry for everyone I'm offending with my awful accent. These Widmanstaten patterns, if we see them, then we know that that wherever the Widmanstaten pattern has come from, probably originated from a meteorite out in space because of how slowly the thing has cooled. Metal on Earth cools much quicker than a lump of rock surrounded by a vacuum because it's in space. So we can find old metal tools on Earth with this pattern. Now you can make similar patterns to this, but not the same as a Widmanstaten pattern. The Widmanstaten pattern means that the metal has actually come from a meteorite, and we've found old tools that are made from metals that originated from outer space. I find that fascinating. I really do. Now the specification appears to just sort of repeat itself. It wants us to talk about the ecliptic again. We kind of already talked about that in a previous video. So why reinvent the wheel? I'm using the same slides as last time, and let's go through this very, very quickly. The ecliptic is the plane around the sun where all the planets orbit. That's the plane of the ecliptic. It is 23.5 degrees roughly from the celestial equator. The celestial equator is an imaginary line in space that we can draw if we stand on the Earth's geographical equator and just look straight up. That line across the sky directly over the geographic equator is the celestial equator, and 28.3 degrees, 23.5 degrees from that is the ecliptic. So I've just stared directly at the light and I can't see anything for a moment. And because all the planets orbit in the ecliptic, then we see interesting things along the ecliptic when we look from Earth. For example, the planets. And because the planets appear night by night by night to move their position, everything along the ecliptic gets special names. They're interesting things. So we've got various constellations. Actually, these are sort of asterisms that are drawn here that are found within certain constellations. They've got special names. The zodiac signs. Really, they're just constellations, or asterisms, should I say, that are found along the ecliptic. Okay, so here's a little animation showing the planets so that you get the idea that they're all in the same plane, but because it's horrifically out of scale, it's not to scale. Let's try and move on from that. Oh, look, here's another one that's horrifically not to scale, showing you that the planets that are nearer are moving faster than the planets that are further away. Oh, look, here are some planets as we see them on Earth, but it's a straight line. That's because we're using a fisheye lens. That's why the horizon looks so curved. So they appear as a curved line across the sky. And here's another picture without the labels, and you can see there's sort of a curve there. There's also a wispiness to this as well. I don't know why that's there. There shouldn't be that wisp. Well, maybe there should be. It's not the Milky Way. The Milky Way doesn't lie along the ecliptic. So here we go. This is where it gets really complicated. Halley, sometimes pronounced Haley. I'm going to call the physicist Halley from now on rather than Haley, although I believe both pronunciations are acceptable, is credited with measuring the size of the solar system. But actually, it doesn't seem like it was him that did it. And everything I saw suggests that all he did is popularize other people's methods. So it's a bit weird that actually Halley's method is where it's listed in the specification. But we'll go with it. So here he is. There's Halley, Edmund Halley. His spelling seems to be different wherever you look for his name. Even he himself changed the spelling of his name a few times because there was no standard in spelling back in the 1700s. Well, late 1600s, early 1700s. He was an astronomer, very famous astronomer, made famous now, of course, because there's a comet named after him called Halley's Comet, although he didn't actually get to see it. And what he did is he used Newton's laws of motion to predict when that comet would be seen next, which is why it's named after him. He's actually one of the people that helped fund Newton's publishing of the Principia. This is one of the big works in physics. This is one of the crowning achievements of classical physics was Isaac Newton's work, which outlined the laws of motion. So according to what I'm supposed to tell you now, Edmund Halley used the transit of Venus to determine the value of one astronomical unit. Actually, doesn't seem like it was him that did that, but okay. And it is a bit of a complicated one to get your head around. Now, the exact method that I'm presenting here might not be the exact method that Halley used, or in fact anyone else that Halley was ripping off. But they used the same idea. The point is that if we look at the transit of Venus, better define that term, a transit is when you see a planet pass in front of something else, the sun. So the transit of Venus is when we see Venus pass in front of the sun. And we could see it as a black dot moving across the celestial, the solar disk. I shouldn't say celestial, the solar disk, the disk of the sun. A black dot moves across it slowly. That's the transit of Venus. Now, the idea is that if we are in different places on the Earth's surface, then we're not all going to see the same transit of Venus. In fact, if we are at different latitudes, the transit of Venus will appear to be at different latitudes on the sun. The issue is that because of the sizes involved and the distances involved, that teeny tiny difference in the latitude of the transit on the surface of the sun, of the solar disk, that teeny tiny difference we're not going to be able to measure. If we could, then we could use similar triangles to work out what the distance is between Venus and Venus and the sun. And if we know the distance between Venus and the sun, and we know how many astronomical units it is away from the sun, which we do know because we can easily measure the time period, the period of orbit of Venus, and we know Kepler's third law, then we can work out what one astronomical unit is in, well, kilometers or whatever. But you can't measure that distance. So what can you do? Well, we can measure times much more accurately with a stopwatch. We can measure to the second or even more precise than that. So when we're looking from above, we've got two places on the Earth's surface. And I apologise for the colours I've chosen here, red and green. I know some people will be unable to see red and green, so I will point to the bits that are red and green in the hope that that helps. So what we've got here is Venus in three different positions. Remember, it's moving across the sun as viewed from a particular line of longitude on the Earth. The red is a more northerly latitude than the green. So we start by seeing the green one here, moving across the sun like this. But we don't see the red one until a bit later because it's not got as far to go. Okay, so that's the colour scheme I'm using. Here's the diagram when viewed from the side. So we've got the distance between the Earth and the Sun. This is not to scale. We're labelling that E. The distance between Venus and the Sun, let's label that V. You'll notice that, hang on a minute, the Sun is curved. So, how can we easily say that, where do we line up these arrows? Look, the Sun is so big. Remember back to the earlier picture, that curvature is so subtle at this sort of distance, it's not going to have that much of an impact on your results. So the distance between the Earth and Venus, I've labelled it here E minus V. It's the distance between the Sun and the Earth. Subtract the distance between Venus and the Sun. So what could Halley actually measure? Well, he could measure the time period, the orbital period for Venus. It was 0.62 years, and from that, in astronomical units, Halley could work out the distance V in astronomical units. But he wanted to know what one astronomical unit was in kilometres. So this is Kepler's third law listed here. These are, Earth is one astronomical unit, therefore Venus is 0.72 astronomical units. The other thing that Halley could measure is this delta L. If we pick two places on the Earth's surface, we can measure the distance between those two places. Now again, we've got to be a bit careful about this because the Earth is curved. But the small difference isn't going to make that much of a difference. We can actually correct for that later on. But let's just deal with delta L as a straight sort of line like this, measured perpendicular to this green line here. Let's keep it as simple as we can and build complexity in later if we want to. So we know from basic trigonometry, just looking at this triangle here, that this capital phi, capital phi, one more time, capital theta, this capital theta here, is going to be the same as this capital theta here in terms of angle. So we've got delta L, difference in latitude, and we've got this E minus V. So we've got this lovely equation here. If we knew what E minus V was, great. We've solved, in kilometres, great. We've solved what one astronomical unit is. So what else could Halley measure? Well, here's a diagram where I've massively exaggerated the distance between these two lines. These two parallel lines, the green one labelled B here, and the red one labelled A here, they're going to be much, much closer together. So close that we can't measure the angular distance between these two. What we can measure is the angular size of the Sun. It's about half a degree angular size. We can measure the what theta is here. We can't measure a difference between these two angles. But what we can do is we can measure, if we draw a dot here to here and then draw one down like this with a line parallel like this on a diagram, that theta there we can actually measure. Quite careful measurements, and it's not going to be wonderfully accurate. But we can't measure the difference between this angle for the green R and the angle for the red R, and we can call that difference delta. We can't measure that. We can measure the transit time. We can measure how long it takes for Venus to transit from this point here across the Sun, the solar disk, to this point here, and we can do that for A and we can do that for B, and we can get a difference in those times. Okay, because these huge distances we're talking about, an angular size is going to be proportional, a change in angular size is proportional to a change in the tangential size, the distance. So if I am looking at the Sun and I move my eye down 1/4 of a degree, then I've moved down a certain distance on the solar disk. If it's half a degree for angular size, 1/4 of a degree, whoop, that would take me here. That would be the half, that would be the radial distance from the centre of the Sun to here. This dotted line is just parallel to the transits, and it just passes through the centre of the solar disk. So we can say that R, the radius of the Sun, of the solar disk, rather than giving that as a distance, we can give that as an angle, and we can say that's about half of the angular size of the sun. So I said about 1/4 of a degree, a little bit more than that. So what else can we measure? Well, there's things we can't measure. Let's just look at those. We can't measure the distance L2 or the distance L1. They're too similar. We can't really measure them in any meaningful way. We can measure the transit times, as I've already said. We can't measure those distances. And we know that Venus will move across the lunar disk with the same speed, whether you're looking from the position that gives you the red line, A, or the position that gives you the green line, B. It will be the same speed that Venus moves across. Now, what that means is that the distance L1 is going to be proportional to T1 because it's the same speed. You can see that L1 divided by L2 is going to be the same as T1 divided by T2. Now we're going to throw some maths at this thing. Let's go for it. Let's throw some maths at this thing. This is a right-angled triangle here. We've got X labelled here. We've got R labelled here. So let's call that angle inside there theta. And we can therefore say that X equals R cosine theta. No one disagrees with that. We can do the same thing with the green triangle here. We've got a little y here. It's a right-angled triangle. R is the hypotenuse as it was before. The angle now is going to be theta plus delta. So we can say that y equals R cosine theta plus delta. Great. Okay, well, because this has got two angles, we can use a trigonometric identity to separate those two angles. Now, I'm not going to do a proof of that in this video. I might do it later, perhaps in a different video. But this is a standard trigonometric identity moving from this line here to this line here. You can look up that standard identity. What else do we know? Well, we know what this length here is. Actually, we don't know this length, but we do know the time, which we're calling T1. And we know that if the speed that Venus moves across is v, then the total distance from this point to this point is going to be v T1. So this distance here is half of that. So this distance here, we can again use trig. This time we're going to use sine. The sine of the angle theta is going to be this distance divided by the radius. So we can rearrange that to get this equation here. So what can we do there? Well, we can make T1 the subject. We can multiply through by 2 and divide through by v, and we get this equation here. Nearly there. Okay, we can do exactly the same thing for T2. So for the time it takes to move from here to here, we can do exactly the same thing again. So the total distance from here to here is v times T2. So half that distance is half v times T2. Rearrange it, we end up with the equation at the bottom here. Remember, the angle was theta plus delta. That's the angle of this green right-angled triangle. We've now got an equation using cosine, an equation using sine for the green triangle here and for the red triangle there. Lovely. At the bottom here, I've just got that capital theta is x minus y. And that goes back to this idea here, where this is capital theta. That's going to be the same as this small distance between those two transits, which was x minus y. That will be the distance between this point and this point, that small distance there. We need some more maths then, don't we? Because we can make this picture easier. This is actually quite a horrible thing to analyse, but delta is really, really small. And for really, really small angles, you can see that the cosine of a small angle is pretty much 1. It doesn't change very much. But the sine of a small angle changes quite a lot. If you change that small angle, the sine of that small angle changes quite a lot. It's a linear relationship. So cosine of a small angle, we can sort of replace that with just the number 1. It doesn't have that much of a difference. As I've said here, the difference between 0.8 and 0.9 is not that big. Difference between 0.1 and 0.2, well, I mean, 0.2 is double 0.1. It's a significant difference. Well, so what that means is that if I've got an angle that's very small, then cosine of that angle is very close to 1. So I could just say cosine of that angle is 1. Okay, it's not quite 1, but let's just say it's 1. But because the sine of that angle varies a lot depending on what that angle is, small little differences in that angle have a big impact, we better keep sine delta in our equation. But the cosine deltas we can replace with the number 1. So I've gone and done that here. I've got rid of the cosine delta, replaced it with the number 1, so that's just turned into this equation there. More maths. We love maths. Okay, so remember that x and y are distances, but we can use angles as well, because at that very, very small angles, distances and angles are pretty much directly proportional. They are directly proportional at very small angles. So because of that, we can say an angle equals a distance minus a distance. We can do that because as long as we use our angles in radians, they're directly proportional. And this was x and this was y. Well, great, let's just substitute them in and we end up with this equation here. And this equation here can be tidied up. We can factor r out of this equation, end up with this. And look, cosine theta minus cosine theta. It's gone. It's gone away. We're left with this equation here. That's exciting. So we now got theta equals r, which I can measure, sine theta, and I can measure theta, sine delta. Can't measure what delta is, not yet. Well, I wonder if I can get another sine delta from somewhere to substitute in. So that's where we take the other two equations, the sine equations I mentioned before. So these were those two equations. I've written them here. Which one's got our delta in it that we can maybe get a sine delta out of? Looks like the one on the right. So let's fiddle with that a little bit. Two angles added together. We can use the trig identity. Here it is. This is what you look up. What sine of the sum of two angles? It's going to be the sine of one angle, cosine of the other angle, plus the cosine of the first angle times the sine of the other angle. So again, you can look this up. Derivations are online somewhere, and I will record my own video of that at some point. Just as before, cosine of delta. Look, delta is going to change a little bit. Cosine of delta is going to be 1. So let's just substitute cosine delta as 1, and we end up with that equation there for T2. And it's got our sine delta in it. So let's just write a bunch of equations again, so we've got them in one place. Capital theta is x minus y, fine. Capital theta is r, sine theta, sine delta, fine, we had that before. These are my two equations for t, the ones of T1 and T2 we just looked at just a moment ago, fine. Now, delta t, the difference in time between the transit when I'm at position A and when I'm at position B, when I'm at latitude A and when I'm at latitude B, is going to be this. I've substituted in the time t2 and I've substituted in the time t1. I've ended up with this expression here. And we can do some maths. What I can do is I can factor out the 2r over v, and I end up with a sine theta and a minus sine theta, which cancels, and I get this line here. Right. Well, that line there's got a sine delta in it. That's encouraging. Another thing I can do is I can say that divided by t1, a sort of a ratio. The difference in times divided by the shorter time. A sort of a how much bigger is the big time as a fraction. That's what we can calculate there. Delta t over t1. Because we can measure these times, we can calculate that. So you know what? Why not? So there's the delta t equation that we've just got here. Here is the t1 equation that we got here, which we got from the previous, well, one of the previous slides. The 2v over r's cancel, and we are left with this. Now you can see they've got a sine theta and a cosine theta. We could turn that into a tan theta if we want to. We don't have to. We could turn it into a tan theta. We could just leave it as it is. It doesn't matter. But we've got our sine theta there. That's what matters. Because we didn't want to get rid of that. So here's that equation written again. This time let's rearrange it to get that sine theta as the subject so we can substitute it. So here we go. So we're taking this equation, we've times through by sine theta, we've divided through by cosine theta, so we've got this equation here. We can now substitute that sine theta into that equation for capital theta that we had before with that horrible pesky sine theta. Oh, it's too many letters. Let's try that again. delta. We've rearranged it. We've got the sign delta here. We're going to substitute that sign delta into one of the equations we had before for capital theta with that pesky sign delta in it. And we end up with this expression here. Okay, if you can't see where this came from, bear in mind that this was just sine theta times sine delta. Capital theta equal to, let's go find where it was. Here it was. Capital theta equals r sine theta sine delta. We've just taken that equation and we've substituted in the sine delta that we've just computed. We've put it in there. We end up with this expression here. Great. Now what? Now, we could do sine over cosine equals tan. We could do that if we want. We've still got a sine theta there. But the point is I can measure theta. And I can measure r. And I can measure delta t. And I can measure t1. Therefore, I can determine capital theta. So, these are some data I stole off the internet. I don't think it really matters. It's all in the public domain anyway. So nothing here is copyrighted. It says transit time in Durban, I don't know where that is, and transit time in Cairo. These 2 points are on the same line of longitude. They're different latitudes. So in this particular transit of Venus, the angle theta was measured to be 46.62 degrees. That's really precise. I'm surprised by that. Maybe it was a modern measurement. Remember the angular size of the sun, 0.2625 degrees. And the distance between these two places is 6,662 kilometers. Let's just chuck all those numbers into that equation, and we get capital theta equaling 0.00547 degrees. Like I said, that is a very small angle. So the curvature of the sun, the curvature of the Earth is going to be insignificant in these results. Or is it? We'll come to that later. So now what we can do is compute EV with that equation we had before. Here it was. We can chuck in our delta L, we can chuck in our tan of that teeny tiny angle, and we end up with E minus V equaling 69,800,000 kilometers. But remember, E minus V was the same as 0.28 astronomical units. So we can do a quick conversion here. This number of kilometers divided by this number of astronomical units, where that's one astronomical unit is going to equal what that is, because I'm cancelling those units, and you end up with, well, nearly 250 million kilometers. That's a bit bigger than it should be, isn't it? In fact, it is. It should be around about 150 million kilometers. So we're not a million miles away, but it's still not really right. Not a million miles away, though. We know that the moon isn't just there, and the sun isn't just there. We know they're a long way away, and we can use that with Kepler's third law to work out the size of the solar system, to work out the distances to all the other planets, which can be known in astronomical units because of Kepler's third law. Right, so we need to figure out why our number was so much bigger than this number, than the accepted number. And there's a lot of reasons. Firstly, we didn't take into account the fact that Venus itself has an angular size. So there are 4 points of contact. So the first contact, second contact, third contact, and fourth contact during a transit. First contact is when Venus just touches the edge of the solar disk. Second contact is when it's just fully inside the solar disk. Third contact, just touching the other end of the solar disk where it's leaving. And fourth contact when it's left. So one way to deal with this is to just use the second and third contact, but instead of using capital R as the size of the sun in our calculations, let's go back a few slides here, we take that in a little bit. We bring it in by the radius of Venus, or the angular size of Venus. So R will now become R minus R in all of our calculations. That's one thing. There are other issues. For example, we've got the fact that while the Venus is transiting, Earth is moving. Venus is moving. Earth is rotating as well. So there's a lot going on here, which means we've got to correct our calculations. It says here about the curvature we still need to include. It hasn't even mentioned the fact that orbits aren't circular, they're elliptical, so we need to take into account eccentricity. Well, Edmund Halley, very clever physicist indeed, was able to make certain corrections that are well beyond the scope of GCSE astronomy. These sorts of corrections. And his value was just 3% out, just within 3% of the accepted value, which is fairly wonderful. Not bad. Far better than ours, where we didn't deal with it. There's other issues as well, by the way. As Venus approaches the edge of the solar disk, the shape of the eclipse, if you like, the Venus occultation, warps, it distorts. So the exact timings can be difficult to measure as well. Anyway, doesn't matter. Now, at this point, for reasons I don't know, the person writing the specification thought, hey, let's just start talking about why there's water on Earth. I don't know. So let's just talk a little bit about why there's water on Earth for a second. Okay. Where has the water come from? So we tend to say the Earth is 4.5 billion years old. Actually, forming the Earth took some time as well. So, as I wrote here, accreting the material takes some time as well. But in that early time of the Earth, the temperature was far too high for liquid water to be on the surface. So you wouldn't have had water, liquid water on the surface. So there are a few different theories about where the water came from on the Earth. It may well be a mixture of lots of different theories. One of the ideas is that the Earth accreted that water as it formed in that what we call the protoplanetary disk, the material that formed the planets. There may have been ice and other particles of water around that got scooped up as the Earth formed, and it's just always been there since the beginning of the Earth. And there is some evidence for that. We can look at a region where it's similar conditions to the protoplanetary disk, the asteroid belt, and there are isotopes of water, so mix of isotopes. Remember, the water is H2O, but that hydrogen has a small proportion of deuterium in it, an isotope of hydrogen that has a neutron in the nucleus. So there's evidence that because the isotopes found in the ice in the asteroid belt sort of similar composition to on Earth. Maybe that's what happened. There's also evidence that that's not what happened. There's always contradictions in these things. You know, if we look at certain isotopes of noble gases at different layers of the Earth, we'll find that the crust is actually different mixture of isotopes. So it actually formed later, we think, than the very middle of the Earth, or the very middle of the Earth. There's some theories about Jupiter. It's not always had the stable orbit where it currently is. There are times when it was far closer to the sun, perhaps even as closer to the sun than the Earth is. And that means that there may have been other icy objects as Jupiter moved in its orbits, drifting around. The other icy objects that were brought in from the outer parts of the solar system, brought in by Jupiter, bringing them to us here at Earth. We think by isotope analysis that there's only about 1% of Earth's material that was brought to the Earth after the moon formed. So when the moon formed, that's when pretty much what the Earth's made of, including the water, that's when it's here. But the formation of the moon, we believe, was caused by a giant impact with a protoplanet called Theia. And so maybe if that protoplanet came from the outer solar system, that brought the water in. But there's a lot of speculation here. Oh, look, a beautiful picture of Theia striking the proto-Earth. I'm not sure how good this artist representation is. Doesn't matter. Let's move on. So let's have a look at these three theories. I'll isolate them here so you can see them. The water's always been there. Smaller bodies dislodged from orbit brought the water, or it was Theia that brought the water. Theia? I'm going to go with Theia, that brought the water from the outer solar system when it collided. Okay. So what are the studies that we can do? Well, we can look at, as I've already mentioned, the isotope composition of that water. If we look at that, we can see that the composition that you would find in comets can only really account for about 10% of water on Earth, which is still quite a lot, but only 10% of the water on the Earth, we think. I'll let you read what's there. I'm not going to read the whole thing to you. But it's interesting that older asteroids have the same sort of composition as, the isotope composition as the water on the Earth. I find that interesting. The picture, by the way, is showing some formations on the seabed. These formations of basalt, they form when you have magma coming up under a body of water and solidifying. And we've found these in all sorts of places across the Earth, suggesting that there have been large bodies of water all over the place for a very, very long time in Earth's history. So, no idea why the origin of water on the Earth needed to be talked about, but we've done it. So now let's move on to making observations. And the best tool we've got to make observations, it's quite difficult to make observations without it, is this thing. It is the eye. The eye itself as a tool has a tiny little hole that lets light in. It says there it's around 3 millimeters. Of course, it changes with the iris contracting and dilating, but there we go. Very, very sensitive. Can detect just a few photons at a time. It's an incredibly sensitive instrument when it's well looked after and when it's dark adapted. The maximum sensitivity is at 507 nanometers, and this is apparently what that color looks like, although obviously screens will render things differently, so that might not be very accurate. And the most sensitive part of our eye, where the rod, I don't care about the fovea here, which is full of cones, the most sensitive part for rods, which are the cells that detect which are not dependent on color. I'm mangling my words here. Let's try this again. There are 3 different types of cone cells, but only 1 type of rod cell. The rod cells are more sensitive in low light than the cone cells, but the cone cells are sensitive to different bands of wavelengths. So we tend to think of those as the cells that are responsible for detecting colors, different colors. I'm saying cells, perhaps I should say receptors in cells. I'm not a biologist. I'm not sure if there's a difference. And if there is a difference, I'm sure some biologist will go into the comments and let me know. Okay, so solid angle, I mentioned there. A body with too small a solid angle, we probably won't be able to see. What is solid angle? Solid angle is how big it looks in the sky, a sort of a 2-dimensional version of an angle. You can see here a solid angle represented as a cone. So what we need to do to see things that are too dim or too small a solid angle, what we call an apparent size, what we need to do is get more light. So here we've got a picture that shows a scene in the background and just a lens being held up. And you can see that the image here is brighter than the image behind because more light is being captured. So the part that's capturing the light we call the objective, either an objective lens, if it's in a lens, but it might be a mirror. So we're just going to call it an objective element if we want, in some sort of instrument that collects light. And the more light we capture, the brighter the image will be. Telescopes usually have much bigger apertures than our pupils of our eye. If you've got a telescope with a 3 millimeter aperture, that just means a hole that lets light through. That's not a very good telescope. You might want to invest in something a little bit better than that. Okay. So we're going to have to talk about lenses here. Lenses are covered in GCSE physics now, but if you are studying double science instead of triple science, I think that's what people usually call it, then you might not actually study lenses. Lenses are actually quite a complicated topic. So let's just assume we've got some thin lenses and have a look at some examples here. You can see they look like an absolute mess. There's rays all over the place from the top of this object, producing an image here. This one, I've picked 2 points on an object to try to see where those rays go, and we can see an image forming somewhere in here. And it's the same thing here with an object here producing an image here. But there's a mess. So we need to really simplify what lenses are. One way to simplify it is by just using 3 principal rays when determining where an image of a lens will form. You know, if you want to do this and draw 1,000,001 rays and try and work out where each ray goes, you have at it. You can do that all you like. But you don't need to. You can work out where the rays will all end up going by using just 3 principal rays. So the principal axis goes down the middle. There's a lens. In these cases, these are convex lenses. The object is placed here. This yellow spot is what we call the focal point, and I'll talk more about that in a moment. But anyway, light will take an infinite number of different paths. We're just going to look at 3 of them. We're going to look at a ray that's parallel to the principal axis, which is a sort of a line of symmetry or that goes through the middle of the lens. We're going to look at a ray that goes straight towards the middle of the lens. And we're going to have a look at a ray that passes through the focal point on the same side as the lens as the object. Those are the 3 rays we're going to look at. So the one that's parallel to the principal axis will end up going through the focal point on the far side of the lens. The one that goes straight through the middle is undeflected. The one that goes through the focal point on the near side will end up parallel to the principal axis. And all 3 rays will cross, producing an image here. If my eye was over here, I would see the rays emerging from this point here. My brain would think that that is the object. In fact, it's an image. So it looks like the light is coming from there. It's actually coming from there, but our brain doesn't know that, so that's the image. So what do you notice about the image? Well, as the object moves towards the lens, the image moves away from the lens and gets bigger and bigger and bigger. But when the object is closer to the lens than 1 focal length, that's the distance to the focal point, then all of a sudden the image ends up on the other side of the lens and is the same way up as the object. Okay, so that's with convex lenses. Here I've got a picture of a ray diagram for a magnifying glass. Just a simple magnifying glass. To make a magnifying glass work well, you have to place the thing you are magnifying closer to the lens than 1 focal length, which is the distance to the focal point. Now, when you do that, it looks as though the rays are coming from some point further away, but it also looks like the thing you're looking at is bigger. It can make it easier for your eyes to focus, but it can also make it easier to see detail because the image is bigger than the object. That's a simple magnifying glass. That's how it works. If you don't like using rays that seem to pass through no lens, bear in mind this is just another symbol for a lens. It doesn't matter. They're only principal rays. If you want every ray to pass through the lens, you can pick 3 other rays if you want, but they're more difficult to trace where they're going, but you'll get exactly the same picture. The ray from here appears to be coming in this direction here. Actually, it comes from here, but gets focused by the lens. So can we use a magnifying glass with distant planets? Well, no, because the focal length is far shorter than the distance to the planet. So because of that, the image becomes a real image, and it becomes much smaller than the object. So it's a much smaller image. The object is a planet in this picture. But because the image is real, we can use that. A real image can be thought of as an object for another lens. So what if I looked at this image with another magnifying glass? So I could now get this image closer to the lens than 1 focal length. So if we've got an object far away, you get a very, very small image. Far too small. But it gets closer and closer to the focal point, which means that we know where that image will be. We can plan for where that image will be. If the object is essentially at infinity, so far away it's at infinity, the image will be at the focal point. That's what the focal point is. It's the point where the rays will converge from infinity, where the rays from infinity will converge. Okay, so I'm trying to show that with this sort of animation. The further the object, the closer the image gets to the focal point. Here's a diagram, but you have to get the idea of the reversibility of rays to understand what's going on here. If I place a light source at the focal point, then the lens produces parallel rays. In reverse, parallel rays, so that's rays from an object infinitely far away, will all focus to the focal point. That's where the rays will converge. So that's how you can measure what the focal length is. So if we use the first lens as an objective lens, so it captures lots of light from a distant planet and produces an image. Now, rather than putting the planet, almost infinitely far away and having the image as a dot on the focal point, which isn't very easy to see, I'm going to use this as a telescope for, I don't know, looking at a bird in a tree or something. So it's a bit closer. So you're going to get an image forming about here-ish. Fine. We look at that image with another lens. So here's the image becoming the object for the next lens. You notice it's in exactly the same place. This is to help you understand how to construct a telescope. Here is the object. That's the thing you're looking at. A bird in a tree, a planet in the solar system. Here is my objective lens. The objective lens captures the light and produces an image, a real image, because of how far away the object is. I look at that real image with a second lens, an eyepiece lens. Because I can arrange it so that eyepiece lens has the object, remember the image from the first lens, closer than a focal length, I can produce a virtual image which is really, really big. Altogether, it looks like this, which is quite difficult to get your head around what's going on. So that's why I sort of broke it into two parts. And I think that really helps to understand how a two-lens telescope works. This particular type of telescope is called a Keplerian telescope, named after Kepler. It uses two convex lenses like that. We don't have to use lenses, though. We can use mirrors, because mirrors can focus light in the same way lenses can. If the mirror is curved in the right way, then you can reflect light through a point, a focal point. Just like this. Parallel rays can focus through a focal point. The curvature of the lens has to be, the mirror should I say, has to be quite carefully designed. It actually has to be parabolic, which means the shape of a parabola, not spherical, to get a nice crisp image to form. And there's clever reasons for that, which are on the scope of what we wanted to talk about today. But here are the three principal rays for a mirror being used as a lens, a curved mirror, a concave mirror. You can see parallel to the principal axis through the focal point. That sounds familiar. Through the center of the mirror, and then the angle of incidence equals the angle of reflection, similar to what we had with the lens. And then through the focal point, then parallel to the principal axis. Again, that's the same as what we had for a lens. So it's almost the same thing. If I have an object, such as something far away like this, rather than using a lens to focus the light, I could use a mirror and get a real image forming here, which I can then look at with another lens, with a convex lens acting as a magnifying glass looking at this image, just like we had for the Keplerian telescope with two convex lenses. If I were to draw all of the rays, it would be really difficult to understand what's going on. But I'm showing you this diagram because what I want to show is that we can actually block part of this off without it affecting the image too badly. How do I see this image, unless I'm in the way? The light is coming from the object, reflecting off the mirror. If I want to do something with that, I need to be stood here with a magnifying glass, or somehow reflect that light out, which means putting mirrors in the way. So it turns out if I block off light here, there are still rays that make it if I block off some of the light. I've just picked a couple of them here. there's a ray that comes all the way from up here from the top of the object and arrives down here at the bottom. Even though I've blocked that off, where the image is, I've said let's block all light at that image, we still produce that image even though it's in the way of the light moving to the lens, to the mirror. Amazing. So what we can do is we can either put a mirror here to reflect the light back through a hole in the lens. I keep calling it a lens. It's a mirror, a curved mirror. Or we could put a mirror here at an angle, reflect the light off somewhere, and then stick a little eyepiece lens up there instead. And that's why there are so many different designs of telescopes. Because that's two different types of telescope you can have with using a mirror for a lens, but there's also different variations you can have if you just have lenses. This is a Galilean refracting telescope, so it uses glass lenses, not mirrors. Now, unlike with the Keplerian, it's a mouthful, unlike with the Keplerian telescope, it does not have a two convex lenses. It has one of these lenses as a concave lens. And there are advantages to this, there are disadvantages as well. The diagram is complicated. What you need to know is that another piece of glass is used here to reduce certain aberrations, and that a concave lens is used as an eyepiece lens, and that's a Galilean refracting telescope. The Keplerian refracting telescope is, as you've already seen, two convex lenses, although here it's shown where they're not biconvex, they've only got one convex side, but that's okay, it doesn't matter. So we've already seen those. With the Newtonian reflecting telescope, rather than producing the image here, we use a mirror to reflect the image up here, then place an eyepiece lens here, acting as a magnifying glass, looking at that image so that you can magnify it. So that's what we've got with a Newtonian reflecting telescope. Reflecting because it uses a mirror, unlike refracting because it uses lenses, refracting because it uses lenses. It's all very logical. The other one, I need to get the pronunciation of this correct. So here is a Cassegrain telescope. That's my best attempt at French pronunciation. Cassegrain. Cassegrain. I just like saying it now. The Cassegrain telescope. This one has a hole in the parabolic mirror. Light is reflected through that hole in the main objective mirror by another mirror, the shape of it slightly different, and then we use an eyepiece lens to view the image just as we did last time. So that's a Cassegrain telescope. I've heard it pronounced Cassegrain, but that's not it at all. So, some quantities, some concepts with telescopes. One of them is light grasp. How much light the telescope can grasp. But basically, how big is the hole that the light can go in? How much light can you grab? And that is proportional to the aperture size, the size of the hole. The bigger the hole, more light goes in. So we say that the light grasp is proportional to the area of the aperture, and that's going to be proportional to the square of the diameter of the aperture. Okay. Field of view for humans is about 120 degrees. But the thing is, with the field of view, even though I've got a diagram here showing a solid angle, which we measured in a unit called steradians, rather than normal sort of two-dimensional, well, one-dimensional angle, two-dimensional angle, which we would call it's two-dimensional angle, which we would call, we would measure in radians or degrees or even gradians, if you like, suffering. 1 gradian is 1/400th of a circle. There are 4 gradians in a circle. 400 gradians in a circle. No, steradians is the unit for solid angle, but actually field of view tends to be given as just a simple two-dimensional angle, a sort of a horizontal, oops, hit my microphone, a two-dimensional line showing your field of view, 120 degrees, fine. So the resolving power tells you about the small detail that you can see. Two stars that appear to be very close together may appear as one star when using this instrument, the eye, When using a telescope, you might be able to resolve more detail and see that it is in fact two stars, maybe a binary system, or maybe just a double star. So resolving power of a telescope is something we can actually calculate. Sometimes we call it sort of the resolution of the telescope. Better resolution means you've got smaller angular resolution. We can resolve smaller distances between objects. You see the picture on the right, on the left here at the bottom. Those two stars are so close together, that just looks like one star, whereas here they're far enough apart that you can resolve that into two objects. So we can use something called the Rayleigh criterion to work out what angular resolution is. Now, where does this 1.22 come from? It's complicated. Something called a Bessel function. Feel free to look it up, but it is, as you might have guessed, beyond GCSE astronomy specification. Usually, because 1.22 is only a little bit more than 1, and this is an approximation anyway, we'd usually say, well, look, it's about this. So lambda is the wavelength of light that you are looking at coming off of some object, and d is the aperture diameter. The bigger the aperture diameter, the smaller the angular resolution, which is better. It means we can resolve objects that are closer together, and so on. Okay. There's also the calculation of magnification. At the bottom of this picture is a very large radio telescope. You probably can't tell easily, but that is huge, a huge dish, parabolic dish. We're not going to go through the derivation of this equation, but magnification is the objective lens focal length divided by the eyepiece lens focal length. It's not too tricky a derivation, but this is a long video as it is. We just don't have time to go into it right now. So Galileo, we have to understand Galileo's contribution. He got hold of this telescope, and what did he do with it? He proved, if ever you could, that the sun is in the middle of he thought it was the universe, that the planets go around the sun, not round the Earth. And his evidence for this were the phases of Venus. He spotted a bunch of other things as well. For example, evidence that not everything revolved around the sun. You know, we've got moons orbiting Jupiter. The idea that the Milky Way's got stars. It's not just a band of cloud. But the phases of Venus are the really exciting bits. So you can see here we've got our... pardon me. Here you've got our sort of schematic at the bottom showing the Earth, the sun, and Venus in these different positions. And we can't see Venus when it's on the far side of the sun. Not really, because the sun's in the way. It's daytime. But when this Venus gets to here, we can see Venus transiting past the sun, perhaps. Or maybe it's just close enough that with a good filter blocking out the light from the sun, we can see an annular shape of Venus. You'll notice that the crescent shape gets, the size of Venus, the angular size, gets larger and larger as the crescent gets thinner and thinner. And looking at this diagram here, it becomes obvious why that is. Venus gets closer to the Earth, that's why it looks bigger. But because of that, less light from the sun is able to reflect to the Earth, so the crescent gets thinner. And the only way you can explain these observations of Galileo is if Venus orbits the sun. So that was a sort of a big deal. Not epicycles around the Earth, Venus orbits the sun. So Galileo, Newton, Kepler, and Cassegrain, they've all got these different telescopes, and there are loads more designs than just those four. There are advantages and disadvantages for them all. So let's just look at an example here. Let's look at reflecting telescopes. The image on the top right, you can see this is with a good quality telescope. This is with a very poor quality telescope. And the colours are distorted, as well as the shapes, but the colours. You've got a bit more red at the bleeding through the edge here and a bit more blue bleeding through the edge there. If you look really closely, you'll see that that's what's happened. A bit like the TikTok logo. It's what it always reminds me of. This is called a chromatic aberration. This happens because the refractive index of glass is slightly dependent on the wavelength of light. So red light is not bent as much as blue light. So the focal length for different colours of light are different for a lens. Now, you can correct this to some sort of extent by placing another piece of glass like this, and you've seen that with the Galilean telescope. But this is one way of correcting it. But it's not a perfect correction. It doesn't fix the problem. One thing you can do is to only view one particular wavelength using filters. And then get a nice crisp image with one particular wavelength. So you view different wavelengths separately and then combine the image later, which is something that people do. Okay, so what's the advantage of a reflecting telescope? We've already talked about getting rid of chromatic aberrations. They don't happen with mirrors. You don't get this problem with mirrors, only with lenses. Another advantage of reflecting telescopes is you can have much, much longer focal lengths. And the reason for that is it's really hard to make thin, very subtly curved lenses. Really hard to do that. The thinner they get, the more fragile they get. So in order to grind a really sort of small, so very large radius of curvature, a very little curvature lens. It's odd that large radius of curvature means less curvature, but that it does, yeah. You imagine the lens is part of a larger circle. Larger radius of that circle is less curvy. Anyway, so that's quite hard to make. So we can do it much easier with mirrors, for a start. We can grind them with a big fat substrate behind them where the light never goes to keep them nice and structurally sound. So you may say, well, why can't you just use a big glass block and then just curve it on the top edges a little bit to keep it nice and strong? No, because then you get other aberrations. All our equations here are based on thin lenses. When you get thick lenses, you get spherical aberrations and other things occurring which make your image blurry as well. So other advantages of reflecting telescopes. You can make really big lenses. Okay, they're not lenses, they're mirrors, but you can make them really big. With a refracting telescope, the objective lens is on the end. Because the objective lens is on the far end, when you pick it up and point it somewhere, the far end is very heavy. So because the far end, let's take this bit here, really, really heavy, you're going to have lots of metal to support this. It's going to be structurally very difficult to build, and there's a limit to how big you can make that glass before it's just too heavy. So here we've got an example of sort of a solution shining the light through the telescope using a mirror to reflect light into this telescope. I think this might be the biggest telescope at the Great Exhibition in the year 1900, although apparently I've cut off the edge that tells you how big that lens is. Let's see if I can... Yep, so here it is. The lens for that telescope at the top right here is 125 centimeters in diameter. That is huge chunk of glass. It's heavy. So the telescope had to be laid down flat. The Yerkes Observatory, you can see here, that's got a 102 centimeter lens. Just before the turn of the previous century, the century before that. And this is sort of the largest telescope that was pointing upwards. They're just too big and too heavy otherwise. But when we use reflecting telescopes, so we're using mirrors, we can make lenses. Look at this, 820 centimeter lens. It's not a lens, it's a mirror. And we can lie at the bottom. It's not big and heavy and has to go at the top end. It could just lie at the bottom. So that's amazing. Here's a comparison of different lens sizes, mirror sizes, should I say? And you can see that some of these are quite large. We've got somewhere in here. Where is it? You've got the Hubble Space Telescope here, which is, it's pretty large, but it's not mind-blowingly big because they had to get the thing up into space. But you've also seen, these are all optical telescopes. There are radio telescopes that are, huge things that occupy mountainsides. The James Webb Telescope is here. The James Webb Telescope has lots of different mirrors connected together. So there's another way of making even bigger mirrors is using multiple mirrors. And you can see there's some proposed telescope designs there that get even bigger than the James Webb Telescope. So that's all very well and good with telescopes, but what if we actually want to go to these planets or comets or asteroids? We want to go there and have a look at them a bit closer. Well, you need to understand what we mean by this. There's no point trying to get closer to the stars. They're just too far away. There's just no point. So when we talk about getting closer to bodies, we're not talking about stars. We are talking about things in our solar system. And we can get closer to certain interesting things. There are a few different ways of doing that. Here is a list. You do need to know this list. There are 4 different types of probes: the flyby probe, orbiter, impactor, and lander. But bear in mind that probes can do, stuff can do 2 things. Probes can do more than one thing. You may have an impactor and an orbiter together, for example. So there are sort of advantages with the flyby. I mean, you can read these. There's no point me just reading this to you. So if you want to, pause the video at this point if you want to make a note of any of this. But this is the sort of stuff, I think a lot of this is common sense. But you need to know this sort of stuff. I do think it's worth pointing out things like the high failure rate for landers. It's, trying to get something to land. And then what we're trying to do at the moment, get things to take off again and bring stuff back to Earth, is really quite tricky to do. Orbiters, believe it or not, use a lot of fuel because you've got to put yourself in orbit around a planet. So that's definitely a disadvantage to them. But you do need to have examples of each, and you are told which examples you need to know about. So flyby, you've got New Horizons. New Horizons, which took these beautiful pictures of Pluto. You can also see a volcanic eruption coming from Io, one of the moons of Jupiter, right here. This is not a volcanic eruption of, magma. This is water erupting from the surface of Io. It's amazing. We've got loads of information about Pluto now. The idea that it's probably got or had an underground water system. It's pretty incredible what New Horizons has discovered. We've also got Juno going to Jupiter. This is a pretty big deal. This is a picture of Jupiter that you don't often get to see. One of the poles of Jupiter. I'm not sure which one it is, actually. No, it says North Pole. This is the North Pole of Jupiter here. Better pictures than we've ever had. We've also got things like the auroras of Jupiter we're able to visualize as well. And water near Jupiter's equator. Fascinating stuff. This is the Dawn Orbiter. Idea of going to these asteroids and to Ceres as well. Took this lovely picture of Ceres, which conspiracy theorists love because it looked like light was being emitted from the surface of Ceres. Maybe there's life there. No, there's not. Well, I hope there is, but I doubt it. Very strongly doubt it. The idea that you've got this sort of hydrated and carbon-rich material on Vesta. Hydrated, wet, carbon-rich. That sounds like the ingredients for life found in asteroids. Fantastic. Ceres, evidence it had surface water at some point in its past. And yet that poor thing got demoted to asteroid. Shocking. For there to be surface water, it has to have an atmosphere. You can't have surface water without an atmosphere. So there's a lot that going on. Impactor. I love that little video clip at the bottom of approaching this comet. I think it was going for the comet called Tempel 1, and it crashed right into it as it was supposed to, kicking up lots of stuff off the surface and from deeper into the deeper under the surface. And then the probe that was orbiting, because the impactors have to have 2 parts to them, the part that crashes into the body and the part that goes around the body, scooping up what flies off it. And it found that the surface is fine powdered ice, but that there were underneath that complex organic compounds. These are things that you would think wouldn't be able to form because of the radiation bombarding, the solar radiation bombarding these bodies, but underneath the surface where it's protected, these organic compounds. Organic doesn't mean living. Organic just refers to using sort of carbon molecules with hexagonal rings. I'm not a chemist. Organic chemistry isn't about life. Biochemistry is. So there we go. That's what this impactor discovered. We've got some landers. So the Philae lander. We love the Philae lander. The lovely video of people getting very excited when it successfully landed. Wasn't a perfect land. It bounced a few times before the harpoons got it to stick onto this comet. But the Philae lander, yes, it worked. It managed to land. We landed an object on a comet. You can see it just here. That's a photograph from the orbiter going around the comet where the Philae lander was, taking a picture of the Philae lander wedged right down there in that crevasse. That's lovely, that, isn't it? And discovering what comets are, and discovering that they're not actually just big balls of snow. There's lots of rock there as well, which was fascinating, and more complex compounds found than you might realize. So, how do you get from Earth to another celestial body? Well, this is a rehash of stuff we've talked about before. I've done this in an earlier video. Can't remember which one, but we've got the derivation of escape velocity. This here is the definition of gravitational potential, the energy per unit mass moving from infinity to a point in space. This is another equation for potential as a function of the distance from a big mass, assuming that's the only mass in the universe. Then our energy to get to a certain point in space, you can think of that as a gravitational potential energy, is actually this equation, not mgh. That doesn't take into account the fact that g gets smaller the further away from the Earth you get. Why we get rid of the minus? Because we're just going to look at a difference in energy as we are ascending, so we don't have to worry about the minus. That's going to be equal to the kinetic energy. We should say that the potential energy we gain is equal to the kinetic energy we lose. So we equate these two, rearrange it to get the speed as the subject, and that is the speed a body would have to move to get away from some mass, maybe that's the Earth, and never fall back. Superb. We've looked at this before, how escape velocity varies. It drops the further away you get from the Earth's surface. But at this point here, the escape velocity is still pretty high, and that's 10% of the way to the moon. So essentially, you can't just get lots of kinetic energy on Earth and shoot yourself up into space. Although there are teams trying to do that, using a centrifuge to fire very small satellites up into space at incredible speeds. But the escape velocity is about 11.2 kilometers per second. Just think about that speed. 11.2 kilometers in 1 second from the surface. Not taking into account air resistance. Straight up to get into space. That's about 25,000 miles per hour. That's incredible speeds. And if you get up into a jet and think, well, if I'm higher up, it's less. It's not that much different. It's still rounded to 11.2 kilometers per second, the escape velocity. So we could do a quick G-force calculation. I think I did this in a previous video as well. What if we wanted to accelerate up to the escape velocity and then drift all the way to the moon? Well, okay, we could use equations like this. In fact, we can't really use equations like this. Because acceleration isn't uniform, but let's pretend it is. Let's imagine we're applying an engine force from our rocket that produces uniform acceleration. We could rearrange it to get this, assuming we're stationary to begin with, so u equals 0. That equals this. That's from the substitution of what v is from the previous slide, the escape velocity. Big R plus S, so, big R is the radius of the planet, S is how far away from the planet we want to go, and you end up with a graph that looks like this. Apparently humans can withstand up to 9G G-force. I find that hard to believe. The maximum G-force humans can survive is about 9G, but that's not for very long. But, maybe we don't need to accelerate at 9g for very long before we reach the escape velocity. Well, let's find out. We plot a graph of g-force versus the height away from the Earth, where we're going to stop accelerating to drift to the moon. And you'll see that it goes down quite quickly. That sounds quite promising. If we have no distance, we want to accelerate to the escape velocity in 0 distance. That's obviously undefined. It's an asymptote that goes off to infinity g-force. If we wanted to basically shoot ourselves up to the escape velocity in the distance between the Earth's surface and the highest jet flight, well, in that case, it's 212 g. Now, maybe some machinery can survive that, but humans definitely can't. We're soft and squidgy, and you'll end up with person soup in the spaceship. So 9g is about you'd have to travel about 630 kilometers, constant acceleration, and then switch your engines off if you wanted to experience just 9g. So that is doable, although we'd probably go a bit further than that, so we're not withstanding 9g. To put this into comparison, 630 kilometers, these distances are in meters. So you can see the ISS is here, 630 is a bit further than that. So you have to go further than the International Space Station whilst constantly accelerating at 9g to be able to switch your engine off and then just drift off into space. Well, that's not a problem. I mean, we went with lower g and greater distances when we visited the moon, but that's not a problem. We did that. So one of the things to bear in mind is in this equation, we said S was how far we've travelled for this part of the equation, and we said S is how far above the Earth's surface for this part of the equation. Actually, that's not quite what, displacement doesn't equal the height. It's not quite the same thing because we launch our rockets at an angle. We launch our rockets at an angle, actually, so we get a bit of a push from the Earth. We've got some initial velocity from the Earth's surface because it's rotating. The Earth's rotating. So that certainly helps. So what does it mean to go to space? It depends on your definition. Different rich billionaires have claimed to go to space, with other billionaires claiming they haven't. It's what billionaires do when you've got billions of pounds. You can ignore the plight of people who are starving, and you can build rockets and pretend to go to space. Anyway, so the edge of space, by some definitions, is 100 kilometers high. ISS, a bit further than that, 4 times further out than that. So rockets are a little bit more complicated than just big explosion, shoot a thing in the air, because what you end up doing is carrying lots of empty weight. So you jettison empty fuel tanks. So you've got less mass to have to accelerate. So you need less force to get the same acceleration. But we don't actually use the same acceleration all the way up. This is a picture of us jettisoning part of a rocket ship. So there's a lot going on with how to get into space. Newton's third law. I wouldn't be a physicist if I didn't talk about Newton's third law as often as I can. Inside the rocket motor, the exhaust, the gas, heats up, causing it to expand in all directions. As it does that, the gas pushes the rocket engine up, and the rocket engine pushes the gas down, which is why you see this exhaust pouring out the bottom very, very fast and very, very hot, is to produce a reaction force on the rocket upwards. That's what it's all about. So, person soup, we don't want that, so we can't have too high an acceleration, but we can just have greater distance over which we accelerate. We have gone to the moon, so it is possible. It talks about long-term exposure here. So short-term exposure to radiation carries some danger. Long-term exposure carries more danger. So we want to avoid that as much as possible. Shielding a spaceship in lead makes it very heavy, which makes it difficult to get into space and expensive. So we can't really do that. That's not an option. There's other bigger problems than that, though. Going to the moon, that was a few days locked in a small container with a few people. You can kind of cope with that. Go on longer than that, it starts getting a bit difficult. Someone's habits are going to irritate you. There's going to be severe psychological problems. People will start hallucinating. Could get very ugly. Then there's the issues with the human body. We haven't evolved to survive in zero gravity. We've evolved to survive in this nice place where we're nice and heavy. If you are not constantly pushing against your own weight, your muscles start wasting away. Your bones become weak and brittle. So It is far easier to die in space than it is to stay alive in space for that sort of reason. So given the difficulties of putting humans in space, why bother? Well, there are some advantages. If something breaks, humans have got very good fingers to repair things, brains to follow instructions. There's only so much you can do with robotics. Humans are more dexterous, I think that's the word, so they can repair equipment that robots can't necessarily do. They can do experiments that humans can't, that robots can't necessarily do. They can think for themselves in a way that robots can't do. But there are other advantages as well. My personal favourite is the fourth bullet point on this list, inspiring the next generation of physicists and engineers. This is something I'm afraid often gets overlooked. The Bloodhound Project is good at doing this. And even things like CERN do a very good job of inspiring the next generation of physicists. There was a huge spike in the number of people studying physics and engineering after the moon landings. At the moment, we're in a bit of a lull, so we need something to get people excited about science again so people will study it. Otherwise, we're going to have too few scientists. And another one that I quite like, the idea of international cooperation. If you've got a bunch of people in space, they have to look after each other. Russia and Ukraine are at war, but on the International Space Station, there was still cooperation at the time I was recording this. Hopefully they still are. So let's talk about that mission to the moon, or those missions to the moon. The Apollo space program. So this is thanks to JFK saying that before the decade is out, they were going to put boots on the moon, a man on the moon. Imagine that in 1960. We're going to put a man on the moon. And they only went and did it. But it wasn't plain sailing. It really wasn't. The Apollo 1 mission, it didn't even get off the Earth, and astronauts died in that. So it was a risky business, but it was necessary. One of the reasons why it was felt necessary is because of the Cold War and the threat of annihilation, of global annihilation. So trying to divert attention to a different competition than just let's build bombs bigger than your bombs so we can all die. So over the 3 years that the Apollo missions were landing on the moon, 12 astronauts walked on the moon. 24 people visited, 12 people walked on it. The reason why more people visited than walked on it is because sometimes, for example, Apollo 13, all 3 of them went round the moon but didn't actually land. Apollo 11 landing in 1969, and Michael Collins staying on the command module as Neil Armstrong and Buzz Aldrin take their first strolls, but that's not all they do. They start leaving experiments behind. And Apollo 12 and Apollo 14, Apollo 15, they leave experiments behind to that we can still use even today. So these are called the Apollo Lunar Surface Experiments Package, although the Apollo 11 one had a different name, the Early Apollo Scientific Experiments Package. But the ALSEP consists of a rather long list of experiments, and I've tried to summarize it here, what different things could be done. Looking at the internal structure of the moon with those 2 experiments, flux of charged particles on the moon, measuring the pressure of the atmosphere. It's very, very thin, but can we measure it? The rate of cooling of the moon. Now, lunar ranging experiment, the laser ranging experiment with retroreflectors, that's still there. You can still reflect lasers and time the delay in a laser beam being transmitted and received off the moon to measure the distance between the Earth and the moon. So you can read all those here. You don't need me to read those for you. Loads of experiments, and you need to know about them. I don't think you need to know them in this much detail, but you do need to know a bit about them. So these are the things that were studied with the ALSEP and the AESEP. And that's it. That's the end of chapter 11. It's a long, long chapter. Chapter 12 will be a bit shorter. Chapter 13 is a long one again. I do intend to finish all of these. I know often people leave comments saying, when's the next video coming out? They take a long time. This took me many weeks to put this presentation together. I've now been recording, according to this clock, for 3 hours. I now need to spend many hours editing this down a bit so I can put this online. So I am planning to make all of the videos, and all of them will be available for the GCSE Astronomy, but it does take some time. So please do be patient with me. I'm doing this as a hobby and I'm working on it as much as I can. And if you've not seen some of the other things I'm offering, look, go to my website, www.physicswithkeith.com. I'm offering tuition. There's loads of videos there. I've started a podcast as well, which hopefully will be available on various podcasting apps very soon. I'm hosting it on SoundCloud. I only get 3 hours free on that, so I might have to start paying for it. So, do go on to Patreon if you want to support that. But I will say no more, because I want to edit this video. Thank you for tuning in, and I'll see you next time.